All right, so now we're ready to talk about the exponential growth and decay model. This is an interesting example because of the result. The result is something that you probably will recognize, and hopefully from seeing the result and how we get there, will clarify a lot of questions you might have had in earlier coursework. So you've actually seen these types of problems before. The differential equation that we're dealing with is going to be dp dt equals kp. And what this says, I've taken this and I've written out in words for you. So remember, a derivative is change. So the change in population, that's the dp, with respect to time, is and equals proportional to the population. So we've got a constant multiplied by the population saying proportional to the population. So the change in population with respect to time is proportional to the overall population. And so let's go ahead now and actually solve this differential equation. It is separable, and so we can go ahead and separate as we've done in the past. To get started, on the left, I'm going to have a 1 over p dp equaling k dt. So think about what I did there. All I did is I divided the p off so I can get my p's on the same side, multiplied the t over. Remember, that's a constant, so that can go anywhere. It just makes most sense to leave it here. So we're set up now as a separable differential equation, and we're ready to integrate. So I'll integrate both sides. On the left, I'll have the natural log of the absolute value of p equals, and over here, we're going to have a kt plus c. Now, in the last example, I mentioned sometimes these differential equation solutions are in such a way where you can solve for a particular variable, and this is one where we will want to carry it a little bit further. I'm actually going to solve this thing for capital P now. In order to do that, though, we'll have to use a little bit of algebra. I'm going to raise both sides of this equation to the e, so e raised to those things. Okay, the reason why I've done that now is because on the left, you can see you would come up with this capital P. On the right, you would still have the e raised to the kt plus c. Then we're also going to use the principle in the last problem to break this stuff apart. So we've got our e raised to the kt now times e raised to the c. Well, this e raised to the c here, this is a constant itself. So maybe I'll call that c1 now. And if you look at this general solution now to the differential equation, this is actually your A equals PE raised to the RT formula. Now, we've used different variables, but it still represents the same thing. We saw this example when we talked about continuously compounding interest problems. We talked about it when we looked into exponential growth and decay back in college algebra. So this formula that you used back in algebra is actually a solution to the differential equation where the change in population with respect to time is proportional to the population. So it's a really, really nice full circle event here that we found. Okay, so now let's take a look at another interesting differential equation. This is Newton's law of heating and cooling. And so, much like the last one, I've got the differential equation written out, and then I've got an explanation of what it all stands for. And so the change in temp T, capital T, okay, the change in the temperature, capital T, there's our derivative, with respect to lowercase t time, so the change in temp T with respect to time is proportional to the difference, there's our subtraction there, between the temperature of the body, capital T, and the temperature of the surrounding medium, T sub m. So the change in temp cap T with respect to time, lower t, is proportional to the difference between the temp of the body and the temperature of the surrounding medium. Okay, so we'll go ahead and solve this now. Once again, it's separable. We'll go ahead and solve this, and then we'll take a look at an example because you might not have worked as many of these in college algebra as you would have, or as you can at this point comfortably. So I'll go ahead and I'll separate. And in separating, I'm going to have a 1 over t minus tm dt equals a k d lower t. So now, once again, ready to integrate. On the left, we'll have the natural log of the absolute value t minus t sub m. And on the right side, we'll have a kt plus c. So remember, when you integrate here on the left, the only thing you care about is this cap t right here. So you could use a u sub here if you wanted to, letting u be this bottom part, but then you would find out du equals dt, and then when we back substitute, we end up with this. So if you need to pause the video and work this out on the side, by all means, feel free to do so. On the right side, it's pretty straightforward. It's a constant. You're with respect to t, so you have your kt, and then I added the c over here. And then much like the last one, I am going to take it a little further now and get myself in a position to solve for t. So if I e both sides, on the left, I've got a t minus t sub m equals e to the kt plus c. I'm also going to now, on the right, rewrite that as c sub 1 e to the kt. So this thing right here, I'm rewriting just like I did in the last part. And now I'm also going to add the t sub m to the other side. So now, this formula right here, which is one you might have seen in an algebra class, is the solution to the differential equation for Newton's law of heating and cooling. So I'm going to go ahead now, clear the screen, and we're going to take a look at a problem and actually work this Newton's law of heating and cooling. All right, so you can see the problem that we're going to look at up on the screen. It talks about being a part of a murder investigation and wanting to figure out when the murder took place. So in this particular problem, we are going to be using Newton's law of heating and cooling. And so let me throw that back up here on the screen. We've got T sub m plus C sub 1 e to the kt. Now it's going to be important again to really understand what all of this stuff means and what it stands for. Where I want to start is the T of t. So this lowercase t right here, this represents the time. Okay, so the temperature at time t. So in this particular problem, there's two things that we know. The initial temperature was 32.5 degrees. So you can see here, the temperature of the corpse was 32.5 degrees at 1:30. Then it was 30.3 degrees an hour later. So T sub 1 equals 30.3. We also know that T sub m, right, that's the temperature of the surrounding medium. We know that that's going to be our 20, and the temperature of the surroundings was 20 degrees. So there's our 20. Now, as you look at this problem, I want to point something out to you. I'm kind of avoiding the differential equation, and the reason is, as I don't need it. I've already solved the differential equation. We've got a general solution right here of the differential equation, and so provided the information that we were given is adequate, we can just jump strictly to this, and now it turns more into an algebra problem. And after having gone through the problem now and identified these pieces, I'm able to plug in what I need, and then in order to get out what I'm looking for. Okay, so let me go ahead and take this information and plug in what I know. As a more specific case now, I've got T of t equaling 20 plus C sub 1 e to the kt. Okay, so all I've done is I plugged in that 20. What I'm going to do now is set up a system of equations using these 2 points. T of 0 is going to be 20 plus C sub 1 e raised to the 0, and then we'd have T sub 1 equals 20 plus C sub 1 times e to the k. Now the T of 0, we know equals 32.5, and this one we know equals 30.3. So again, to come up with these, all I did was substitute the 0 and the 1 in for the t. So when I plug it in here, you get the 0 there and the k there. So now, here sits our system of equations. This is going to allow me to solve for my C sub 1 and my k. All right, so I've got 2 unknowns, I've got a system, this is good. So out of this first one here, my C sub 1 is going to equal 12.5 12.5, right? E raised to the 0 is 1, so essentially all I'm doing is subtracting the 20 to get 12.5. For the second one here, if I solve it for C sub 1, it's not going to come out quite as nice, but it's still not too bad. That's going to be 10.3 divided by e to the k. So what I did is I subtracted the 20, and then I divided by the e to the k. When I take these now and set them equal to one another, I'm going to get my 12.5 set equal to 10.3 over e to the k. Now I can solve for k. To solve for k, I'll multiply that over, and I'll divide the 12.5. Then I'm going to log both sides. So when I natural log both sides, this is going to give me k equals the natural log of 10.3 over 12.5. So now that was a lot of the legwork leading us up to actually solving the particular problem that we're interested in. We know that normal body temperature is 37 degrees. We know that the initial temperature was 32.5. After an hour, it dropped to 30.3. So if we want to figure out when this murder took place, we're trying to find a t-value, in particular with the information C sub 1 equaling 12.5, k equaling this, and our temp t equaling 37. So watch, when I plug all this in, I'm going to get a 37 equals 20 plus the 12.5 times e raised to the natural log of 10.3 over 12.5 times t. So I've used this equation right here where my temperature, 37 degrees, is normal body temperature. I plugged that in right there. I know that the temperature of the surrounding medium is 20. My C sub 1 I found was 12.5. My K value I found was this natural log. And now when we solve this, we'll get our T. So this is just going to be a little bit of algebra here. I'll let you guys handle that. Comes out for T to equal natural log of 1.36 divided by the natural log of 10.3 over 12.5. This is approximately 1.59 hours. When you punch this in your calculator, you'll find out that it comes out negative, which is a good thing, right? Because we're essentially kind of backdating this thing to figure out when the murder took place, since the body was constantly cooling. So then the hour and 59 minutes, if you use some unit conversions, this gives us 1 hour and 35 minutes. So since the body was found at 1:30 p.m., if I go backwards 1 hour and 35 minutes, that's going to put us at 11:55 a.m. So again, one of the big takeaways from this is that I didn't actually have to use the differential equation. I could use the solution. The information given in the problem is very, very helpful in getting this original set up. And then it really is just an algebraic problem. Many college algebra courses do cover these types of things, and that's great because it really is just algebra beyond the point of understanding it's a solution to the separable differential equation.